Welcome to the course on this power quality. Today we will like to cover the topic on unified power quality compensator. It is also called typically unified power quality conditioner. The outline of today's presentation, we will start introduction, then we will talk about state of art on unified power quality compensators, then we will give a classification of UPQC, then the principal operation of UPQC, then analysis and design of UPQC, then control of UPQC and modeling, simulation and performance of UPQC with the numerical examples, and we like to summarize the presentation with references like. So, the objective of today's presentation is typically we like to discuss the requirement and applications of UPQC, then we will go to the configuration of UPQC, then we like to discuss analysis and design of these UPQC, and then we will discuss the control algorithms of UPQC, and then method of modeling and control of UPQC like. So, coming to like the power quality in the distribution system, we already discussed about that. In AC power system, we have a power quality at in different part of like a generator, generation, transmission, distribution, utilization, but mainly it is on utilization side in distribution system is the more severe, and these power quality problems are we have already classified, but the major power quality problems are voltage based power quality problem, which can be either both the way, whether it is in supply system due to the natural causes we discuss in detail, or it is due to the probably the caused by the main means because of the load and other reasons like. So, that is about how voltage power quality problems covers typically like voltage distortion, the voltage unbalance, voltage sag swell, and then voltage fluctuations, and then the current based power quality problems also can be like typically your current unbalance, then reactive currents, because majority of the loads are inductive load. So, they draw the lagging power factor currents, and then if it go to like a 3-phase system, then it go to typically you can call it like unbalanced current, and if it is a 4-wire system, then you have a even the presence of neutral current also like. So, we can call it the single solution for both. We discussed already the solution for current based power quality problem, which we discussed in DStatCom. Then we discussed the voltage power quality problem compensation in the active series compensation, or you can call it like a DVR. But now today we will like to discuss as a single solution for both of these problems in the this unified power quality compensators, or in short we call it UPQC. So, this UPQC is a combination of active shunt and active series compensators. It consists of both, because you like to have a by active shunt compensation to mitigate the current power quality problems, and by series compensation you like to mitigate the voltage power quality problems like. So, the shunt device of UPQC, also known as DStatCom, distribution static compensator, mitigates the current based power quality problems, and the series device of UPQC, also known as DVR, dynamic voltage restorer, mitigates the voltage based power quality problems like. These are typical you can call it a block diagram of UPQC. So, you can say we have a supply, typically the distribution grid, in which you can call that we have a normally the voltage based power quality problem. Voltage based power quality problem we discussed earlier also, it may be like a voltage unbalance, as you can say in 3-phase, it can be like a voltage unbalance, voltage distortion, or you can have a voltage sag, voltage swell, voltage fluctuations. These are the voltage based power quality problem, but still we want the grid current should be balanced, sinusoidal, and at unity power factor. That is given the below what is the requirement here like or see you can see. Similarly, if you look into the load side, the most of the loads are very sensitive. They are designed that they should have a balanced sinusoidal supply voltage across them. However, many of the loads draw the non-sinusoidal current. They because of the solid state control into them, or because why we are using a solid state control we already discussed earlier, because the many appliances where we are using the solid state controllers, they are offering a lot of energy conservation to us like even starting like a single phase we talk about like either lighting system, LED lighting system, or you are using a typically like a brushless DC motor fans, or in 3-phase system you are using adjustable speed drive like for air conditioning or many process like. So, they might have a typically like a load unbalanced current, they might have a lagging power factor load, then unbalanced current, and might be having a harmonics also as well as neutral current like. But we want that the voltage across the load should be sinusoidal. So, looking the requirement of the load, that you must have a regulated sinusoidal voltage, balanced voltage across the load, and in spite they might be drawing the let us say not ideal current. I mean, but on the grid side our requirement, even the quality of the grid is not good as far as voltage is concerned, but we want the grid current should be sinusoidal. So, we connect a device here in between, you look into that there are two voltage source converter here, one is a series active conditioner, another is shunt active conditioner, which is a combination of both, which we call it UPQC. So, that takes care of the both the problem. The load could get a good voltage quality, in spite it does not draw good current quality because it is a load of different variety. Similarly, on the grid side, you have a very may not be a good voltage quality, but you expect that the consumer should draw sinusoidal balanced supply current in spite of that at unity power factor like. So, that is the basic operating principle of this UPQC what we want. Of course, there are many manufacturers who are manufacturing now UPQC, it is already in practice used, and there is a typical art that on this shunt device known as DC shunt provide the reactive power compensation along with the load balancing. It also provide neutral current compensation, and if required it may be harmonics elimination also, or you might have a like harmonics also in your load current. The interesting part of it, the design of this shunt compensator or the voltage source or compensator used for the shunt, its rating differs for these requirement. Like if you want more features, certainly you have to certainly allowed to add the cost of this compensator for more features. Typical example I can give you here, if you really do not need harmonics, then probably the switching of the devices at around 1.8 kilohertz or 2 kilohertz will be enough to generate the fundamental current, whether it is for your negative sequence current or it is a reactive current or it is typically neutral current. But if you really want to have a harmonics current generation, then the switching frequency should be at least double than the harmonics you want to eliminate it like but it should be much higher than the if you want to eliminate the higher order harmonic, then certainly it is required that the switching frequency should be much higher, not only 2 kilohertz, but it might be 5 kilohertz or 10 kilohertz. Then your switching losses in the devices increases, which increase the loss, not only the losses, but your thermal design of the converter also have to be enhanced, like a heat sink size increases, cooling fan and all those also. So, cost is certainly getting affected. As a principal circuit will be looks like the same, but the rating consideration differ like Similarly, the series device known as DVR, dynamic voltage restorer, keeps the voltage load and voltage insensitive to the supply voltage quality problems, such as on supply side you might have voltage sag and voltage swell, the voltage surges, voltage spike, voltage noises and unbalanced voltage. But on the load end you have to keep the ideal voltage, balanced voltage, sinusoidal voltage and regulated voltage like. That is the job of your series compensator part like called DVR like also. So, well, as far as development is concerned, these UPQC have been developed in varying configuration, and we have a many advanced control technique for this UPQC. Then there are different solid state devices are used for different ratings in those converters. Then you have improved sensor technology like because we need all the feedback for control like a current signal and voltage signal, and they certainly have to be sensed with quite accuracy and without distortion in their waveform, because it is only the compensation on that. So, normally we use the Hall effect voltage sensor and current sensor for that. So, of course, they are available at now at reasonable price. So, there is no difficulty of. Similarly, your microelectronics revolution, like typically microcontroller and DSP are also available now at reasonable cost. So, we can afford for developing of this. So, this is typically the photograph of current sensors, and these are the typical photograph of a DSP on which we implement the control algorithm like Coming to the classification of unified power quality compensators, these can be classified based on the converter type, whether you are using current source converter or you are using voltage source converter in the configuration of UPQC. So, that is one kind of classification. The another classification can be the topology based classification, whether you are putting right shunt UPQC. Right shunt UPQC in the sense that you are putting a D-STATCOM part on the right side on the load end, or you are putting the typically left side shunt, means you are keeping a D-STATCOM part on the left side of series is on the load side and your shunt is on the left side or so, or you can call it grid side. Then the supply system, you might have a requirement like you are going to have this UPQC for single phase system like a 2-wire system, or you are going to have a UPQC for 3-phase 3-wire system. I mean typically or you have a UPQC required for 3-phase 4-wire system where neutral is also associated there. So, this is another classification for which you require this UPQC like. And then method of control. This is interestingly here whether the UPQC have to control, it called UPQC-Q. UPQC-Q in the sense the injection of the series compensator is at the quadrature only through reactive power. Q means represent for reactive power. So, we control that the series compensation, for series compensation we are using only reactive power. UPQC-P we are using for series compensation only active power. We are injecting active power and by which we are compensating, or UPQC-S. UPQC-S means we are using the for series compensation the injection of the voltage at different angle which may consist P and Q both. Why this concept is there? The rating differs of this series compensator as well as shunt compensator in all three these controls. Like in a practice might be most of the cases we might be operating UPQC-S, but in many situations you will find the rating will be less in UPQC-P. Even operational losses might be reduced by operating in some of these modes like also. So, that is the reason this concept of control have come for these three kind of manner. So, this is typically the block diagram, in general block diagram which may be applicable either for single phase, 3-phase 3-wire, 3-phase 4-wire. So, it is we can call it the kind of converter based classification we will talk about, but however we already discussed this is right hand kind of shunt compensator because D-STATCOM we are keeping on the load side and series compensator we are keeping on series type like, and of course, it using the voltage source converter which is preferred. We discussed already that nowadays we are preferring the voltage source converter in place of current source converter. We will discuss in the maybe next slide. Here the reason being that the device only either diode conduct or IGBT conduct, the losses in the device is less, and on DC link we are putting an electrolytic capacitor which is very cost effective, low cost, low size, small size and almost negligible losses. But if you are taking a current source converter, then you have to use the series inductor which is costly, bulky, noisy and lossy. So, and even weight also like so it causes a reasonable difference, and moreover we will talk about like this is like a current base, you can call it current source converter based UPQC. So, you can see there are two current source converter here and energy storage between it through inductor, reactor or inductor, and designing a DC inductor is not so easy because normally inductor with the DC will saturate. So, you have to certainly put like some small air gap in the inductor so that the value of this inductor does not change even on DC. So, certainly this inductor will be costly, bulky as well as having a heavy weight. So, and losses also. Moreover, when device conduct, because the IGBT cannot have a reverse voltage blocking capability, you have to connect a series diode in addition to that. So, it means when device conduct, the losses of not only IGBT, but the losses are of IGBT plus your diode also. So, losses of both elements are there in that case. Moreover, you have to have a typically the mandatory the capacitor here, you can just see the capacitor here it is, this is the mandatory component which is not necessarily required in case of voltage source converter. So, these are relative merits and demerits. Of course, if you look into this UPQC, it was first patented in 1989 by Bannon. However, later on according to the technology, because when I am talking about like 89 around that time the current source converter were more popular compared to the voltage source converter. But with the time of course, the technology changes according to the benefits of the converter also. But this is the circuit which can easily operate also for the same kind of compensation, but relative merits and demerits certainly give the weight for the typically for voltage source converter based compensation. Now, coming to the like a topology based classification which we are talking about, here if we have a symbolic that we have a source, then we have a source impedance, we have a like a here the typically kind of a DVR, and we have a shunt compensator called D-STATCOM. Well, this topology is preferred in this typically in case of the UPQC which are used in distribution system. The reason being that normally your load having a current based power quality which are compensated by locally by putting D-STATCOM in front of that, by D-STATCOM. Now, the current going into the VR will be minimum because your load may require reactive power, load may require like a negative sequence current or maybe even a harmonics also neutral current, which is compensated by shunt compensator. So, whatever is going into the now in flowing into the let us say into DVR or series element, it is a good quality or minimum current you can call it. So, rating of the your DVR will be certainly minimum. And of course, I mean this DVR responsible that because the grid voltage of the source impedance is not a good quality, might have a voltage sag swell, voltage unbalance, voltage fluctuations, but this inject the voltage like. So, this configuration is preferred because the rating of shunt as well as series will be minimum in this configuration. I mean all the power current which are responsible for current based quality problem are not flowing into the DVR, I mean also. And the voltage another reason is now the voltage across the D-STATCOM is also regulated voltage. But if you put the D-STATCOM on the other side, we will discuss with another topology here. So, it means here the voltage rating of the you can call it the D-STATCOM is minimum and the DVR current rating is also minimum. That is the reason of course, you can call it the rating of overall UPQC also will be minimum. So, this is preferred topology for UPQC as far as distribution system is concerned. The another topology if you look into the which called left hand in the sense D-STATCOM is a left hand on supply side and DVR on the critical load side. This is the topology which preferred in transmission system. I mean because where it came the concept it also called custom power devices, but first this fax devices, this is a category of the fax devices, they came first for transmission system, and transmission system we put a D-STATCOM on substation and DVR in series with the line. So, there this topology is preferred because we have to provide the compensation in the line, but in case here in distribution system this topology is not preferred because the DVR rating I mean like will increase. Why? Because here the current I mean which are to be compensated that also flowing in through the DVR, and the D-STATCOM current rating have to be designed corresponding to the maximum voltage because the voltage here across the typically of the grid is fluctuating. So, you may have a voltage swell, it means D-STATCOM voltage will also increase. So, voltage rating of D-STATCOM will increase like of course, for current it is to be designed. So, here in this topology you can call it the current and voltage rating both will increase like I mean. So, you may find I mean this is good for transmission, but this is certainly good for distribution. So, this topology is more preferred in that case like I mean also. So, right hand side UPQC is considered a better topology, means that is the better topology for distribution system, that is the conclusion of that. And this is the typically actual topology of the you can call it left hand kind, okay, because you are putting a left hand on the D-STATCOM, how to look like a single phase configuration, and we have a like a here the injection transformer for injecting the series voltage also. So, this is just like to have a single phase shunt, you can call it left shunt like here, and this is your typically right shunt. So, you are keeping D-STATCOM on right shunt. So, this is the topology for single phase, and you have a ripple filter here, okay, typically, and as well as a ripple filter here, that we discuss it because you can call it like a, this is supposed to improve the voltage profile across the I mean across the load, and here also you have to improve the voltage profile of the injected voltage in the series with the line, so that the switching harmonics are not injected into it like I mean also. Then we have of course the expansion of 3-phase circuit. I mean this is your D-STATCOM with the ripple filter interfacing inductance which are connecting directly across the load, and the current based power quality problem it is mitigating locally as far as the voltage across the load as well as the D-STATCOM that remains the fixed, that causes the I mean you can call it minimum rating of voltage rating minimum. And similarly the series compensator which are I mean connected in series, it is drawing now current flowing through the series compensator is minimum because the whatever current based power quality problem is there, that is already compensated by shunt compensator. What we are going to save here, we could have used one DVR and one D-STATCOM. What we save, that we put the capacitor in common. Putting a capacitor common, we are saving one capacitor. The another benefit is now we can flow the active power in this way or this way, which we can't do in DVR. I mean DVR we discussed either you have to have a rectifier supported or battery supported or self supported, but in that case there was a limitation that the active power cannot flow so freely. Here you can have a only injection of active power, or you can inject this voltage at any angle 0 to 360 degree, that gives you a reasonable freedom I mean for this circuit configuration in that case. So, that is the reason UPQC considered to be a quite good solution, provided you can probably afford the cost of typically so having a two compensator into one like, but you save certainly some part of the component here. And this is you can think about like a here I mean series is of course 3 wire, but the D-STATCOM you are considering 4 wire system to compensate locally the neutral current also. because that is something like you can think about, I mean supplying the with the this UPQC system like also. Now, that was about the circuit configuration. Now, coming to the rating based classification of UPQC, I mean which is really differ in the method of control, that UPQC-Q, the DVR used in series with the series injection at the quadrature with the supply current with almost 0 active power injection. That is the reason we call it UPQC-Q. Q means the voltage in series is injected at the 90 degree with the current supply current, so that I mean you do not have a typically any active power injection for series compensation. May be applicable, may not be applicable for all condition, for some condition, but in some condition it might give the rating also reduced one. Another is a UPQC-P. Okay. So, UPQC-P means now DVR is used for series injection in power supply, supply current is in active power injection, means series compensation we are doing only through active power injection into it, because now the if need the for series compensator or DVR we need some active power, we can certainly take from DC link, and that is provided by the shunt compensator or by the STATCOM to this. So, I mean practically it is possible that you can inject in phase with the your supply current also, I mean typically. Of course, in many situations it will give you the minimum rating of your series compensator, I mean because you are having a minimum voltage injection, and current of course depends on the supply current, how much power you are trying to also. Another is UPQC-S, I mean this is very versatile combination. So, DVR is used for series voltage injection at optimum phase angle with minimum kV rating. So, there may be many criteria what you really will like to use for UPQC-S. I mean you like to have a minimum VA rating, or you like to put any at particular angle the injection of the voltage, I mean in series, I mean that you can do that, I mean in this UPQC-Q, like because that is, I mean all these modes are possible even as, because you can certainly draw the active power, or you can feed the active power on the DC link, which DC link voltage regulation is a responsibility of series shunt compensator to allow the bidirectional power flow. Series compensator is supposed to do the job for mitigating the voltage based power quality problem by injecting the voltage in series with the line, like I mean also. So, coming to the in first category of UPQC-Q, in UPQC-Q the shunt compensator D-STATCOM is mainly connected across the consumer load at the right hand UPQC, and D-STATCOM is used for all current based compensation of the load end, and DVR inject the voltage in series between the AC mains and the load and at the quadrature with the supply current, and DVR needs only reactive power from the series compensator, which voltage source converter can generate locally. I mean active power it is supposed to take from DC link, but the reactive power it can generate locally, I mean like also. And since the DVR part of UPQC inject only reactive power, therefore, the type of UPQC is known as UPQC-Q. Here of course, the active power we are not circulating through D-STATCOM. Of course, we might have some active power to meet the losses of both the converter, I mean as well as interfacing transformer, as well as the you can call it interfacing inductor and ripple filter, apart from the switching losses in the devices and the electric loss in the DC link capacitor. So, apart from I mean living apart from the losses which you have to feed certainly from through shunt compensator or shunt VSC, but I mean you are not circulating any active power from shunt to from DVR D-STATCOM to DVR, DVR to D-STATCOM in this control like. And this is typically the you can think about the configuration, I mean on right hand side, which we really suggested why we select it. I mean there is no restrictions that you can not select it another configuration, but this is the right hand, the D-STATCOM is typically on the right side, here we are connecting it, and DVR is on the left side, and we have a DC link common like. But of course, what we are saying that you can generate the reactive power locally, this injection is through reactive power, you are not taking any active power, but only you are regulating the DC link voltage with the help of the shunt compensator, which is normally you are doing otherwise into the STATCOM. So, the control goes in that simplified manner for like a single phase load like. And the typical you can call it the phasor diagram, I mean you can look into the voltage here, and if it is a sag comes, then you have to regulate the voltage. So, you have to only inject the voltage which is at 90 degree. So, shunt compensator is supposed to maintain the unity power factor. Okay. You can see clearly unity power factor, the voltage your current is in phase with the voltage, and now shunt compensator job is series compensator job is that to inject the voltage at 90 degree with this current, so that you do not associate any active power for series compensation. So, certainly might be that you can call it this DVR voltage injection may be little higher, we will just look into other case, and but the voltage you can call it is the same regulated voltage which are on this arc. the load voltage will be equal to the source voltage. I mean, even you might have a sag or so, which is regulated voltage. So, that load is not affected by typically by any power quality problem in the supply system, also caused by voltage sag on. So, this is the case typically your think about like a voltage sag, and this is the case of typically of voltage swell compensation, that voltage increases and you have to reduce the voltage to again to coming to the back to the same level like also. So, the operation of UPQC is quite satisfactory for voltage sag compensation, and however, UPQC cannot be used for voltage swell for buck operation except one case which will be discussed in the numerical example. Now, coming to the UPQC-P, in UPQC-P the DVR inject the voltage in series with the in between AC mains and the load and in phase with the supply current and supply voltage. It needs active power from the series voltage source converter operating as a DVR without any reactive power injection through DVR with minimum voltage injection like, and the rating of DVR is also quite low as it required minimum series voltage injection, and since DVR part of UPQC inject active power, therefore, this type of UPQC known as UPQC-P like. So, well, this is the typical case you can think about, like if there is a voltage sag, I mean ideally voltage should be this much, but it reduces because of voltage sag. So, you have to inject this voltage in series with this, I mean by DVR, so that your voltage is regulated across the load. So, you are putting like in series, I mean shunt compensator bringing this current, I mean typically I mean grid current in phase with the voltage, but now series compensator is only doing this active power. From where this active power is coming? It is coming from this active power through DC link only, coming from D STATCOM itself. So, you can call it the this active power is circulating between the two like. And this is the case of voltage swell. I mean you can think about that voltage is going to be up. So, you are going to reduce the voltage with the help of putting this through injection by reducing this voltage to back or so. The UPQC operation is quite satisfactory for both voltage sag and voltage swell compensation, and in UPQC-S the DVR inject a voltage in series between the AC mains and the load and at a predetermined phase angle with the PCC voltage, and it needs both active power and reactive power through the series DVR with minimum rating of both VSC or other criteria decided by the customer. And in this type of UPQC, the rating of both DVR and D STATCOM are minimum or utilized in a proper coordination to supply the reactive power of the both with proper sharing. And series DVR part of the UPQC inject active or reactive power with minimum VA rating. Therefore, this type of UPQC is known as UPQC-S, and the S depends on apparent power, which is a VA rating like. And the typical phasor diagram you can think about, like you can put like a typically if you have a voltage sag, the voltage is reduced for here. Now, you can inject the voltage at any angle and bring the same voltage on this arc, so that voltage is regulated like. So, it means this you can call it this voltage injection is not at the 90 degree or in phase with the current, you can have at any other angle, for which you can understand the how this is not so easy to find out, that the reason being why the rating will be affected of the shunt. I mean when you are injecting the volt typically of series, because the active power of the required for series is coming through the shunt. So, once it is active power flowing through the shunt, it means the shunt rating will increase. I mean that is in case of UPQC-P. Of course, series you might be having minimum, but the shunt rating will increase. So, somewhere this will be a kind of optimum concept that okay, rating of both should be, and normally in general the inventory of these converters are the same. So, you might be keeping like a both rating of the both same in general. Then the question is that you have to utilize the rating of both also. I mean because the some part of reactive power of required for load, you can divert that responsibility for these series compensator also. Not necessarily entire reactive power have to be supplied by D STATCOM. So, that feature is also possible in this like, and this is certainly you can think about like a we have a voltage cell, in place of this voltage going up, now we have to inject the voltage in a such a manner that its voltage comes to the same level like. Okay. So, you are injecting this voltage in that manner like, I mean also. So, it means you can have a sag compensation as well as swell compensation. All compensation is possible by UPQC-S, because you can inject the voltage from 0 to 360 degree, I mean with respect to the current, I mean or voltage. Normally we consider the shunt compensator is already providing the unity power factor operation. So, series will be able to inject voltage at any angle with respect to the current, because now reference for the injection of the voltage normally consider the with the current, because that active power reactive power what we discussed it already like also. And the type of operation of UPQC-S is quite satisfactory for both voltage sag and voltage swell compensation. And typically coming to the principal operation, a UPQC has two VSC connected to common DC bus, and AC side of them are connected one VSC in series known as DVR of AC line through the injection transformer, and another VSC is connected in shunt known as DC term, normally connected across the consumer loads or across the PCC. But if you are applying this at high voltage, maybe that on shunt also sometimes we use the transformer for purpose of isolation and voltage matching. I mean, it depends on the requirement of the consumer if you are going to use this UPQC for very high voltage application, but power electronics you want to design at optimum voltage, which is lower voltage than what really your system is having, where you are going to connect this UPQC like on. So, both these VSC use the pendulum control, therefore, they require a small ripple filter to mitigate the switching ripples of both the converter, and it requires certainly Hall effect voltage and sensor and current sensor for feedback signal for the control algorithm for providing the your switching of the both the converters, and the DSP or like a similar another kind of DSP called D space is used to implement the required control algorithm to generate the gating signal for the solid state devices of both voltage source converter of UPQC. And the series VSC use the DVR normally control in a pendulum voltage control mode, because you are injecting the voltage to inject the appropriate voltage in series with the AC mains. And the shunt compensator, shunt VSC used as D STATCOM is normally control in pendulum current control mode to inject the appropriate current in parallel to the load in the system. Like the UPQC also needs many passive elements such a DC capacitor, DC link bus capacitor, AC interfacing inductor, because you are generating pendulum voltage and you have a sinusoidal voltage on the either the across the load or in the line. So, certainly you need the typically you can call it like a AC inductor to interface this, and you require injection transformer and isolation transformer, depends on series for series compensation, shunt compensation we talk about, and a small passive typically filters across the switching filters kind of thing. Coming to like analysis and design of this typically of UPQC. So, now in this case for looking at design, we will try to take the example of 3 phase which is normally used, or the shunt for 3 phase typically 4 wire. We have like a neutral current compensation also by 4th lag, which we already discussed in shunt D STATCOM, and for series of course, we have to inject the voltage in series line of the series, but many cases in operationally not necessary you have to inject the voltage in all, maybe like you like to if voltage unbalance there, it may be I mean typically maybe the injection may be required only in 2 line, not necessarily in 3rd line. But DC link is a common which exchange the response typically of active power. So, responsibility of regulating the DC link voltage is again the D STATCOM. I mean in the sense that D STATCOM supposed to supply the active power required by series compensator, or active series compensator if it releases the active power, it had to take back the active power to the system back like So, this DC link voltage regulation is a part of your control part of the D STATCOM. The series compensator is supposed to only inject the right voltage, so that the voltage quality are maintained at the point of common coupling across the load. So, design of 3 phase 4 wire UPQC includes the design of D STATCOM and DVR, and the design includes the voltage rating of the voltage source converter of D STATCOM, current rating of D STATCOM, kV rating of D STATCOM, DC bus capacitor calculation, AC interface inductance and ripple filter calculation, and design of your DVR or series compensator include the voltage rating of the voltage source converter of DVR, current rating of voltage source converter of DVR, the kV rating of voltage source converter of DVR, injection transformer rating, of course, its voltage and current rating of both the side and transfer ratio, and DC bus voltage of DC bus capacitor, interfacing inductance and ripple filter design. So, the design parameters of UPQC, the design is carried out considering a right hand UPQC-P. Of course, you can have a design corresponding to any, but you have to here take only some typical example which you should be able to modify according to your requirement. Supply system and load parameter are as follows. So, So, we consider the supply nominal supply is 415 volt 50 hertz with a plus minus 30% voltage variation, which may consist the sag, swell in this range as well as the unbalance. And the line impedance, of course, we are considering some typical value of 0.1 ohm resistance, and the inductance of the source is 1 millihenry. And the load we are considering that it is a linear balanced load of 3 phase 4 wire load of 30 kilowatt at 0.8 lagging power factor, which is also nominal power factor load in general, I mean in practice. And this STATCOM VSC is designed for compensating the reactive power of the load, which is you can calculate from the load, I mean 30 kilowatt at 0.8 lagging power factor means the reactive power certainly you can calculate from this. I mean by taking a 30 divided by 0.8 will be a kVA multiplied into 0.6 or under root 1 PF square will be the reactive power. So, reactive power comes 22.5 kVAr, and allowable ripple in DC link voltage is certainly delta VDC at 5%, and allowable current rating typically ripple current in the D STATCOM is around like a 15% or so, and the allowable ripple in AC current, I mean 10% which is responsible, and switching frequency of order of 10 kilohertz. Like it is just like a guideline, I mean from the design formula, but of course you have to apply your mind as expertise for this. So, coming to as a DC link, this is the formula for voltage source converter, that what should the relation between AC and DC link voltage to root 2 into V line divided by root 3 into M. M is a modulation index, so you can take 1, and it is a system voltage. 415 is the line voltage which you can put. It comes 6 times 77.692 volt, which you can round off around like a 700 volt. So, 700 volt is a reasonably okay voltage if you are really designing for 415 Indian distribution system like or so. So, M is a modulation index and consider 1, and thus the VDC is obtained as 6, and for VLL of 415 volt distribution network, hence it can be selected 700 volt. So, that is about the DC link voltage selection. Once we have a voltage selection, we can find out the capacitance from this dynamic equation. Of course, this capacitor selection can be on so many criteria, but which give you the maximum value of capacitor, that criteria is selected. You can take based on second ripple, harmonics ripple also of this DC link, because that load unbalancing, or you can call it single phase load, you will have or voltage unbalance. So, second harmonics will be there certainly on the DC link of this UPQC, but probably dynamics will give you the more value. So, you can consider that in the dynamics that how much voltage reduction you can allow. So, we say that we can allow the 5% voltage reduction, that is the reason that the minimum voltage from the nominal voltage it comes energy storage within how much period you should recover. So, by keeping this value all in this standard relation which we discussed earlier also, I mean we want in 30 millisecond in 1.5 cycle to recover. So, this capacitor comes around 3090.89 microfarad, and you can select the next higher value typically of 33 in is you can select higher available value as a 3500 microfarad like also. I mean you get a collect, these are design guidelines, I mean, and but nearby you can select it like the value corresponds to that. Like. So, coming to the typically the selection of AC inductor for phase lag, you can calculate LR from this standard formula which is available in many of the text like root 3 M VDC divided by 12 AF Fs into I ripple, and keeping the value like we consider already you can have a 15% current ripple, and you can calculate this inductance comes around 1.793 millihenry, I mean order of that, like I mean for interfacing inductance for that lag. Hence here the modulation M is the modulation factor, A is the you are considering the value of 15% 10 kilohertz, and VDC typically 700 volt and line voltage 415. So, the value comes around 1.793, and normally rounded the value can select the 2 millihenry for this UPQC lag. Coming to the neutral lag, I mean that is virtually we can call it what the voltage can appear across the neutral lag. From this relation and putting the value, you get the typical value of 2.391, little higher than the phase value, and corresponding to that you can select corresponding to around 2.5 millihenry is selected like also. Well, coming to the selection of ripple filter, which we have again discussed in DVR as well discount to find out the noise from the voltage at PCC, the time constant I mean should be much lesser than the switching frequency. So, considering your time constant Ts by 10. So, the RR normally we consider a small capacitance, and CR is the capacitance and TR is the switching corresponding to switching frequency. So, we can find out the impedance corresponding to that, and we can find out this impedance should be quite high I mean normally we consider a typical value of maybe 5 to 10 ohms, and we can find out the capacitance also corresponding to that. So, that impedance is quite low. So, you can find out corresponding to switching frequency, this impedance is very close to resistance, that is 10 ohm resistance. So, it comes 10.41 ohm, and the capacitance value of typically order of typically 5 microfarad, and that give you the impedance for fundamental frequency quite high, 578.832. It comes across the phase. So, you can call it, I mean the phase voltage is around 239 or 240 volt, and you divide 578, it will be half a like a typically ampere, less than a half ampere. When you take a square, it becomes a quite quarter, and the resistance you can call it quarter. So, its resistance will be hardly typically 10 multiplied like a 1/4, so around 2-3, hardly 2-3 watt loss, irrespective of the rating, whether you are designing this UPQC for 50 kV or 100 kV or so. But that improve the voltage profile, because high all switching harmonics, because of this very low impedance like of 10 ohm all get sucked into, but it does not have a much higher energy associated with that. I mean that is more the important in this case like also. So, selection of a ripple filter, we already talk about 10 kilohertz we design, and the ripple filter may be 10 ohm resistance and capacitance of 5.5 microfarad, and the impedance offered for switching frequency is around 10 ohm, and impedance corresponding to fundamental frequency is 578.83 ohm, which is sufficiently large enough, hence the ripple filter draws negligible fundamental frequency current, and that is the reason the losses are also negligible in ripple filter, I mean like also. So, we can calculate even the losses in the ripple filter by calculating the power loss into it, and you can find out the current, I mean divide voltage divided by the current. So, it comes 0.414, and the losses in at fundamental frequency will be hardly your 5 point, all 3 phases it is hardly around 5 watt, not more than that, irrespective of the rating. These are not rating related issues, it is only correspond to the switching frequency like on. And selection of voltage rating of the solid state devices. So, you can call it like a, you are taking a voltage that is maximum voltage in the circuit, the DC link voltage, but then you can have a little overshoot also into that, maybe 10%. So, in place of 700 volt, it will be like a 770 volt, and normally we take a safety factor, we select the voltage rating of the D STATCOM IGBT around 1200 volt also. And current rating, we already talk about that, you might have a typically the nominal current what we have designed plus the ripple current, which we have considered 15%, and you can add this current with that, and you get the peak current, I mean with the safety factor. So, current rating comes around 61 ampere, and you can select the current rating typically for order of 100 ampere. Because this 100 ampere is corresponding to like a 25 degree Celsius, but when you are operating this, I mean the devices around up to 75 degree centigrade. Apart from that, you are going to operate at higher the switching frequency, so device have to be little derated, and that is the reason we select the device of 1200 volt 100 ampere like on. Similarly, we can do the calculation for DVR or series compensator UPQC, the design of injection transformer. So, injection transformer we already talk about that we want a voltage variation compensation of plus minus 30%. So, voltage to be injected will be order of the same. So, that comes around 71.88 volt, and then the current rating of this typically, so that much voltage, and how much you would like to keep on typically on the DC link. So, you can find out the turns ratio corresponding to that. If DC link is decided by shunt capacitor, which is corresponding to 415 volt, like I said, I mean that much voltage this series capacitor is generating like a 415 volt, but you want only typically of 71 or 72 volt. So, that will the turns ratio order of 3 you can have, and the VA rating of the transformer you can find out 3 VDR and IDR, because that series current you know around like a 59.63 and voltage injection 71 into multiplied 3 phases. So, it comes like a 12.8 kVA the rating of the series compensator or DVR, and you can find out the current how much it is, that depends on the load current rating, because the unity power factor current flowing into the line. So, whatever the current is flowing into at unity power factor in the line, that is the current rating of DVR. Now, coming to the interfacing inductance for DVR. So, you already have a like you can calculate current which we already calculated, and then you can find out the from this current ripple and the voltage is typically the, and it comes out of like a 7.86, which you can take 8 millihenry for this, and typically you can find out now voltage rate, typically the voltage rating of the DVR and D STATCOM share the common DC link. So, that is the reason you can find out, we already have a turns ratio. So, we can find out the current on the secondary side of the DVR, and then you have a typically with adequate safety factor the current rating of 32 ampere you can take on the in place of 19.87 ampere, and then you can similarly design the even the ripple filter as we did for again considering the switching frequency of 5 kilohertz here for and selecting the value of 5 ohm and capacitor 6.34. So, we can select the 5 ohm resistance and 10 microfarad for the design of ripple filter also. So, well, this is now we are finishing the design. Thank you very much.